and trying to identify as many patterns as you can for binomial expansions. And there's a whole heck of a lot of patterns, and there aren't necessarily right or wrong answers that I'm looking for at the very beginning. So my first slide has what we're working with today when I talk about binomial theorem. We're talking about expanding a binomial, like this very first piece up here at the top. It says x plus y raised to the n. So x plus y is my binomial because it has two terms that are being added together. That by definition is a binomial. And then it is being raised to some power n, and I could change that, so I'm raising it to the first or the third or the 10th or whatever that may be. And then I have several values already up here. So I have x plus y to the 0, x plus y to the first, x plus y squared, all the way up to raised to the 5th. And I'm going to give you some time quietly by yourself so that you can find as many patterns as you can find. And then I'm going to have you discuss them in your small group. So just going to give you a minute or so to kind of look down the line. From line to line, are you noticing any patterns? From line to line, do you see any patterns? Okay, so now you've had some time to look for patterns on your own. I want you to, in your small groups, talk to each other and list out as many patterns as you can. Listen carefully to your group members. They might be saying a pattern that you see, or they might be saying a different one, and you might need to share yours as well. I'm going to challenge all groups. Can you find 5 different patterns? So challenge your group and see if you can come up with 5 patterns. Go.
And then that like triangle thing where it goes like 5 on the sides, and there's like the 6, 7, and 10s, and then it's like 16.
Okay, let's see if we can share some patterns that we're seeing in Pascal's, in the binomial expansion. You didn't hear me say anything. Give me a pattern, your group top.
Just the first and last
Terms.
are multiplied by 1.
Oh, okay. In each row, the first and the last are being multiplied by 1. I would call it a coefficient of 1. So 1x, 1y, 1x squared, 1y squared, 1x cubed, 1y cubed, 1x to the 4th, y to the 4th. Okay. Good. Excellent pattern. Catherine, give me a pattern.
The x squared and the x and the y in the beginning and the end are the same exponents.
Oh, okay. So like if we're looking at the second line where it's being squared, the first term is x squared and the last term is the y squared, and that continues. So if we look at 5, we start with x to the 5th, and then we end with y to the 5th. Excellent pattern. Allie, give me a pattern.
Well, we said that it was Pascal's triangle.
You said that it was Pascal's triangle. Do you guys remember how to create Pascal's triangle? How do I start Pascal's triangle? Okay, so I usually tell students that you start Pascal's triangle with a triangle of 1s. Right, the first row is 1, and then the second row has 2 1s. It's like the corners of the triangle. Okay. 1, 2, 1. Okay, and then the next line, David said is 1, 2, 1. The middle term there is the sum of the two closest terms to it. So 1 plus 1 gives us 2. And then similar to Nick's statement about the coefficients of the first and last term in the expansion, in the row of Pascal's triangle, it starts with a 1 and it ends with a 1 for all the rows. So then we would have 1, 3, 3, 1, where 1 plus 2 is 3, then 1. Right, where we're adding those consecutive terms and getting those numbers. And you said you saw Pascal's triangle. Can you describe to me where you saw Pascal's triangle? In the coefficient. So, like, if I look at the expansion for x plus y to the 4th, my coefficient is 1, 4, 6, 4, 1, which is this row of Pascal's triangle. Okay, excellent. So, note that I am choosing my first and last term to be x and y, where they both have a coefficient of 1. Therefore, you can see Pascal's triangle. If I were to change one of those terms to be a number or have a number coefficient, like if I changed it to x plus 2 or 3x plus y, we wouldn't be able to as clearly see Pascal's triangle. Would Pascal's triangle be at play? Absolutely, but we might not be able to notice that pattern right away. Okay, so that's a great pattern. Thanks for sharing that, Allie. Taylor, you guys got another pattern for us?
We just said the exponents for the x increase or decrease, and exponents for the y increase.
Excellent. Okay, so when you look at your exponents, and I'll look at the last one with the 5th, she says if you look at all the x's, their exponents are decreasing. The first term is x to the 5th, x to the 4th, x cubed, x squared, x. This is really x to the 1st. So we probably assume this last one has x to the 0. Really, it's just that x to the 0 is equal to 1, so you don't see it, right? And then same thing, but in reverse order, the first term must have a y to the 0, which is really just 1, and then it goes up by 1. Y to the 1st, y squared, y cubed, y to the 4th, y to the 5th. Okay, so good. Descending and ascending exponents. The first term's always going down, the second term's always going up. Trevor, you guys got another pattern for me?
The exponents of each term add up to the original exponent.
That is a great one, and I use that when I'm doing binomial expansion just to kind of check my work and make sure I didn't make a silly exponent error. Okay, so what he's talking about right there is if we look at this last line again with the 5, the exponent in the first term is really like 5 plus 0, which is 5, and then 4 plus 1, which is 5, 3 plus 2 is 5, 2 plus 3, 4 plus, or 1 plus 4, and 0 plus 5. So the exponents in a term add up to the power that you're raising it to, okay, and you can see that in all of the rows. Raven, do you guys have another one? They've all been said?
What we have is that on the second term, the coefficient is always going to be the same as the exponent.
I think that's a good pattern to notice. Okay, so he's saying the second term, so the first one doesn't really have it, I guess, but then you can think 0, maybe. But the second term has the same coefficient as the exponent. So the second term is 1y, has a 1. The second term is 2xy, has that 2, it's the same as the exponent. The third term has the 3x squared y. I use that to help me match the rows of Pascal's triangle. So like if I'm raising it to the third, I know it's the 1, 3, 3, 1 rule. So if you ever used Pascal's triangle in a previous class, that's how I make my connection. So I think that's a great pattern. Any other patterns out there you want to share? Okay, so the next thing I'm going to have you do is you need a calculator today. Please get out your calculators. And I'm going to give each table group a different combination to evaluate in the calculator. And some of you might get one of my easy combinations, so you don't need a calculator if you're familiar with combinations. Okay. So this group right here, I'm going to have you do a combination of 5 items, chosen 0 at a time. So I'm going to have you do a combination of 5 chosen 1 at a time. 5 choose 2, 5 choose 3, 5 choose 4, 5 choose 5. Could you please evaluate that in your calculator?
It's one, I'm right. I know my math.
Okay, Jacob, what did you guys get for 5 choose 0? 1. Jordan, what did you get for 5 choose 1? Carrie, what did you get for 5 choose 2? Emily?
What do you got?
Mitchell?
5. 1.
Why are people OMGing?
Oh my gosh.
It's the next row of Pascal's triangle. Okay, so my math PSA for today is, if you're interested, Pascal's triangle has many more patterns. You can look at Pascal's triangle outside of the binomial expansion. Like we're focused on those expansions of x plus y to the n. But if you look at the triangle, there are so many more cool patterns that you can find. If you're bored and looking for something to do, I highly recommend drawing yourself a little Pascal's triangle and doing some investigations. Okay. So each row of Pascal's triangle is actually made up of combinations. We could use this same pattern to say that this row of Pascal's triangle is really 4 choose 0, 4 choose 1, 4 choose 2, 4 choose 3, and 4 choose 4. Okay, and if you plug those into your calculator, you're going to find out 1, 4, 6, 4, 1. It actually works. Okay. Okay, so the reason why I had you do this then, like why are you looking for these patterns, is number one, to help you self-check your work so that you don't make tiny mistakes, like Trevor's thing about the exponents adding up to the number that it's being raised to. A great way to check your work. But I also wanted to show you this so that you can make the connection to the combinations and understand why the binomial theorem is what it is. Okay, so this is the binomial theorem. I would put this into my notebook. Okay. I'll let you write it down and then we'll kind of say a couple of things about it and then we'll do some examples. Again, this is probably something you have seen before. So as you're kind of finishing jotting down the binomial theorem, I'm going to say this. When I do binomial expansion, I don't actually recall this theorem. Like this is not something that I have necessarily memorized, right? What I have memorized or what I know is those same patterns that you guys listed for me previously. So notice that those things are going to come into play where the things in the binomial that you're trying to expand, the x, the y, and the n. Notice that every binomial expansion will start with that combination of n choose 0. A combination of 3 choose 0, a combination of 10 choose 0, it's always going to be that first one, because how many ways are there to pick nothing? One way, you don't pick anything. So you're always going to get that first term to be 0. Then you notice that you're taking your x and your y, you've got your first term and your second term, and you're going to raise them to different exponents. Just like I think Taylor gave us the pattern for descending exponents for x, means it's going to start with the highest exponent, whatever n was. So if it's raised to the 8th, you're going to start with x to the 8th, or the first term to the 8th. And then it's going to go down by 1 for each term until you get to 0. Okay, so you end at x to the 0. On the other side of that, the second term, which in this case is y, but we can plug anything we want in for those terms, that exponent is going to be increasing. So notice we started at 0, and then we add 1 until we get to the end. Okay, So I think about it in terms of patterns as opposed to memorizing the formula. I would suggest you do the same. It's more likely that you'll remember it in the future as opposed to memorizing that formula. Also, I'll say this. I can do quite a few rows of Pascal's triangle in my head. So I kind of use like that piece that Joe gave us, where if I see that it's raised to the 4, I know that's the row 1, 4, 6, 4, 1. So even though I know the binomial theorem has those combinations, I can just call up on those coefficients from Pascal's triangle and use them in my expansion. So if you also have experience with Pascal's triangle and you prefer to do that as opposed to writing out the combinations and plugging them into your calculator, I am totally okay with that. So I'm going to do an example, and then you'll do an example for practice. The first one that I'm going to do is one where, notice I'm changing my second term. Instead of x plus y, I have x minus 3. That means my second term is actually negative 3 because it's supposed to be a plus. Anytime your second term is negative, that means your signs are going to be alternating in your final answer. So you'll have like positive, negative, for as many terms as you have. If I were going to start this, thank you very much. If I were going to start this problem, I of course would start with that very first combination. Remember, for that combination, you're going to start with your power. So you're going to do a combination of 4, choose 0. And then I'm going to go into my binomial. I'm going to pick up my first term, which is x. And I'm going to use Taylor's pattern, which is it should start with the highest exponent. And that's the same as the power, so x to the 4th. Then I'm going to go into my binomial, and I'm going to pick out my second term, which is the negative 3. Okay. And notice I use parentheses around these things, especially like negatives, or if you have a variable and a coefficient, use parentheses because the power applies to both. And this will be raised to the lowest exponent, which is 0. And then I'm going to go ahead and, for the sake of showing all of my work, I'm going to write out the other terms. The next one I'll do a combination of 4, choose 1. It will be x to the 3rd now because that first part is going to decrease exponents. And then negative 3 to the 1st. Get my next step. Combination 4, choose 2. X squared, negative 3 squared. There's another pattern that maybe we didn't see because we didn't have the combinations, but this is going to be helpful for some examples we do at the end. That other pattern is, notice that the combination I'm choosing, like I'm choosing 0, it matches that exponent of your second part. So if I'm doing 4, choose 1, that's the exponent on my negative 3. If I'm doing 4, choose 2, that's the exponent on my negative 3. Okay, so that's another pattern that you can use, and it will be helpful to us in a few examples. So 4, choose 3, x to the 1st, negative 3 cubed, 4, choose 4, x to the 0, and negative 3 to the 4th. Okay, I always usually, after I write all that stuff out, I do one other check, like just real quick. Are my x's decreasing? 4, 3, 2, 1, 0. Are my y exponents increasing, or negative 3? 0, 1, 2, 3, 4. Yeah, I'm pretty sure I've copied that stuff correctly. Okay. So now you're going to do the work where you actually evaluate each part of that. You know, I'm using Pascal's triangle, so I'm not going to use my calculator. I know a combination of 4, choose 1, or 4, choose 0 is 1 times x to the 4th, and anything raised to the 0 is 1. Plus, this will be 4 times x cubed, negative 3 to the 1st is negative 3. Plus 6 times x squared, negative 3 squared is now a positive 9. Plus 4 times x, negative 3 times itself 3 times is negative 27. And plus 1 times x to the 0 is 1, and negative 3 to the 4th is a positive 81. Now, this again would be me showing all of my work. You know, on your quiz on Friday, I think it would be a good idea to show your work so that if you made one small mistake, I could just take off for that mistake as opposed to not knowing where you got your numbers. I will show you, here's something people in the past have always done. Some of my students say, ugh, that looks like too much. Like there's too much multiplication, there's too much addition, like there's too many things happening, I'm going to get lost. So what some people do is they then group like those three things that are getting multiplied together. So if you like that method, if that helps you keep things organized, like what are you multiplying and what are you adding, group those three things together. There should be plus signs in between those groups of three terms that you're going to multiply together, or three parts that you're going to multiply together. So make sure that you have the plus signs there, and then whatever is in your parentheses or brackets, those things are going to multiply together. So my final answer on this particular problem would look something like this. X to the fourth minus 12x cubed plus 54x squared minus 108x plus 81. And I can do a few things to check, like are my signs alternating because there was a subtraction sign? Okay, yes. Are the exponents from my x going down? Yes. Okay. I could have also done that check that Trevor gave us up here on my work. 4 plus 0, 3 plus 1, 2 plus 2, 1 plus 3, 0 plus 4, is that equal to 4? There's lots of ways for you to self-check to make sure you're getting the right answer. Does anybody have any questions about that? Okay, in your notebooks, I would like you to do my next example. 2x plus y raised to the fifth. Okay, 2x plus y raised to the fifth. So I'll give you a minute or so to kind of get us started, and then I'm going to interrupt you just to talk about one quick thing, and then I'll let you finish it. Okay, so as I'm walking around, I just want to break in right now and say one quick little thing. I see most people writing it, and I talked to a few people who didn't, but I agree that for that very first term that is 2x, when you want to talk about the first term raised to the fifth, then raised to the fourth, then the third, so on and so on, you should include that set of parentheses right there. So that when you evaluate this and you try to get what your actual term is, a combination of 5, 2, 0 is 1. What is 2x to the fifth? What's that, Joe? 32x to the fifth. It's really 2 to the fifth, x to the fifth. Okay? So maybe go back and check. That's a property of exponents. It's called power of a product, where if you're multiplying things inside a group of parentheses, you raise it to an exponent. The exponent really applies to everything. If you're having trouble remembering that, this is how I try to help people remember that they should do 2 to the fifth. What does it mean to do 2x to the fifth? So if you actually did the long work, you would actually be taking 2 times 2 times 2 times 2 times 2, which is 2 to the fifth, and x times x times x times x, which is x to the fifth. So that's going to give you that 32x to the fifth. So you might go back and double check your work. If you have like 2x to the fourth, it should really be 16x to the fourth. Okay. And make that change as needed. And so this is my final answer. 32x to the 5th plus 80x to the 4th y plus 88x cubed y squared plus 40x squared y cubed plus 10x y to the 4th plus y to the 5th. If you're not getting those same coefficients, I'd go back and double check, did you really do 2 to the 3rd to get 8? Okay. Again, I can do some checks, like are my x's exponents decreasing? 5, 4, 3, 2, 1. Are my y exponents increasing? 0, 1, 2, 3, 4, 5. Do my exponents in each term add up to 5? 4 and 1, 3 and 2, 2 and 3, 1 and 4, 5. So I can do some checks to make sure I don't make small errors in my work. Are we okay with this? Okay. Excellent. We have a couple other examples to do which will not take nearly as long, but they're good for us to at least have a conversation about together. So the next example, we'll look at the first one up at the top. So just focus on that one for right now. We want to find the 5th term in the expansion a plus 2b raised to the 8th. And of course, one way to do that would be to actually do the entire expansion and figure out what the 5th term is. But that to me seems like a lot of work, as I'm sure it seems to you. So instead of doing that, what I would do is I know each term is made up of a combination. First term raised to an exponent and second term raised to an exponent. So I'm going to set this up. I know I'm going to do a combination of 8 choose something that's going to get multiplied by a raised to the something. That's going to get multiplied by that 2b raised to something. And so I really have 3 things to figure out about the 5th term. What combination am I taking? Combination of 8 choose blank. What am I going to raise a to, and what am I going to raise 2b to? Any thoughts on that first part, that combination for the 5th term? Combination of 8 choose? There's probably 2 answers floating around. 5 or 4? Give an argument. 4 because you really start at a combination choose 0, right? So think about your very first term. I'm actually going to flip back a page. Okay, think about your very first term in this expansion. The first term is a combination 5 choose 0. The second term is a combination 5 choose 1. The third term is 5 choose 2. So we could argue that if you want the 5th term, you really want to do a combination of choosing 1 less than that. So we would say combination 8 choose 4. Now from there, what I would normally do is, remember I also talked about that other pattern, that this number that I'm choosing always matches the second exponent, or the exponent for my second term. So I would know that at the same time, 2b should be raised to the 4th, and then I can use Trevor's rule about the sum of the exponents have to equal 8, so what should I raise a to? Also the 4th. And then you could put these things into your calculator. I think is a combination you choose 470 times a to the 4th times 16 b to the 4th, and what's 70 times 16? 1,120. A to the 4th, b to the 4th. So that's probably a much quicker method. Can you do some setup for that second one real quick? See if you could do the setup for the 7th term. What would you do to find the 7th term of 3x minus 2y raised to the 10th? See if you can get those numbers correct. And then we'll put up answers and see if we agree. What do you guys choose? A combination of 10, choose 6. So then we know negative 2y is getting raised to the 6, and therefore 3x must be raised to the 4. These exponents must add to be the power of the binomial, which is 10. I got, let's see if you got the same thing, 1,088,640. And that would be x to the 4th, y to the 6th. You know, make sure you have that negative 2y in there. If we were to raise that to an odd number, then we would have a negative term. Okay, so you have to be careful with that. And the last example is it's set up a little bit differently. It doesn't say which term I want, like the 5th or the 7th term. It just says, tell me what the coefficient for a x to the 8th, y to the 6th is. Okay, so we want to know, like, what's the number in front of the x to the 8th, y to the 6th term. But I would sort of think about this in the same light. I want to do a combination of my power is 10 choose something. I'm going to do my first term, which is x squared raised to something, and also y raised to something, and then try to connect the dots. In order to get y to the 6th, what must this y be raised to? Must be a 6. And in order for them to be the same as the combination, then I can plug in my 6 right there. And I know that these exponents have to add up to 10, so this one must be 4. And think about your property power of a power. You'd multiply those, and that's going to give you your x to the 8th. So when you put the pieces together, everything should work out there.
Where does the A come from?
That's the thing you're trying to find, the coefficient.
Oh, okay.
So it's really like saying, like, what's the coefficient A? And so you would really just need to do a combination of 10 choose 6. Yes. In this case, it would be your answer because the x to the 8th and y to the 6th are going to produce a number. Note that if it was like 2y, I'd have to take that to 10 times 2 to the 6th. Okay, and that would be my coefficient. The coefficient is the number that would be multiplied in front of the term. Okay. You do have a homework assignment. It's on the gold sheet. Make sure you do those problems so you're comfortable with binomial expansion. We'll be reviewing tomorrow and quizzing on Friday.